Hello everyone, welcome to Physics 331. I think this is going to be the last video of the course, and I think what I'd like to try to do is just to show you how you can kind of accurately plot some of the results that we obtained in the previous video. The previous video, one of the focuses was to see if we could come up with a prediction for the propagation of pulses along a transmission line. And the scenario was that we had a signal generator outputting a voltage Vg, and it had an output impedance of Zg. What we ended up doing was selecting Zg to be equal to the characteristic impedance Z0 of the transmission line. The transmission line was terminated by a load impedance ZL, and we chose ZL to be real. So it's some resistance that's between 0 and infinity, but it has no frequency dependence like from a capacitor or an inductance. And we were going to measure the voltage at the input of the transmission line, so this Vin. And we did a calculation, and the result that we got was this thing. So at the input of the transmission, we see the original pulse scaled by a factor of 1/2, and then at a time 2L/S later, the pulse reappears, this time scaled by the reflection coefficient gamma over 2. And this time delay corresponds to the time that it takes the pulse to travel the length of the transmission line, reflect off of the load impedance, and then reappear at the input. So before we get to some of this plotting, I was going to just show you the paper that I followed to derive some of these results. And so here it is. This is the title of the paper. I think in the video I said it was a 1969 paper. That was the year that it was submitted, but the actual publication date was July of 1970, and so it's in the Journal of IEEE Transactions on Education. In fact, the author was from Queen's, so Canadian University. So I won't go through the paper, but I can highlight a few things that maybe are familiar, right? So here's the convolution. So here's the convolution notation. And I think somewhere we can probably find some inverse Fourier transform, so there's some inverse Fourier transform. So a lot of the techniques that we used, of course, are shown in this paper. Okay, so let's get to how we might be able to make some plots. So going to search for, here's UBC system for writing Python code in a Jupyter notebook. And so we'll just open a brand new notebook here. And so we'll start by making some notes. And so this is maybe going to be plotting pulse propagation along a transmission line. And so let's just say that this is going to be, this will be for a November 4th, 2021 video. Okay, so first, actually, we can add a few things. So let's first import required modules. So the first thing that we're going to import is going to be NumPy. So we'll import NumPy as NP, and we'll also use matplotlib. So import matplotlib.pyplot as PLT. Okay. And so what have I done wrong? Oh, sorry. It's matplotlib. lib. So let's get that right. Okay, good. So before we get to plotting our pulses on the transmission line, let me just show you a useful function that you might find convenient in certain cases. So we can make use of the Heaviside function to construct a square pulse. Okay, and so let me show you how that works. Actually, so let's first create a list of times and then plot the Heaviside function. Okay, so to make a list of times, I'm going to say that, let's say TT is going to be my list of times, and it's going to be, we'll use the arange function from NumPy, and what we'll do is we'll start from 0, and we'll go to, I think what we'll do is we'll go to 300 nanoseconds in steps of 0.1 nanoseconds. Okay, and so this will be in units of seconds. And then in addition to that, what we'll do is we'll just try this plot. So we'll plot on our x-axis our list of times, and then on our y-axis we're going to use the function np Heaviside. And when you call Heaviside, you have to supply some arguments, and so there's going to be a list of times, and then this 0.5 means the Heaviside function is going to go between 0 and 1, and it's going to make that transition when TT is equal to 0. What the 0.5 means is that right at t equals 0, the Heaviside function will be equal to 1/2. So let's just plot this to see what it looks like and see if we got this right. Okay, good. And so there it is. I can suppress some of that text there. So you can see our list starts at 0, so right away the Heaviside function is at 0.5, and then it jumps abruptly to 1 and is at 1 the rest of the way. If we wanted to delay where that transition is, we could add some things, and we could say, let's make a T0, and we'll say that T0 will shift this by 10 nanoseconds. So this is going to correspond to the start of the transition. Or maybe we'll just call this just the transition time of the Heaviside function. And so all we have to do then is to subtract T0 away from our list of times, and hopefully if we run this, right, so there's our Heaviside function. And so it goes from 0 to 1. Okay. So with that in mind, what we're going to try to do is we're going to try to define a function to plot or let's say to construct a square pulse. Okay, so the notation to define a function is def, and then we'll call our function pulse maybe. And so we're going to have to pass some arguments to our function. One will be a list of times. Maybe T0 will be our start time. And then maybe we'll define the width of our pulse. And In fact, we can also define a height of our pulse. Okay, and so what we want to return from our function is, first we'll start with our heaviside function, and so we'll pass our times, we'll shift the transition using T0, and then we'll have our 0.5 in there. And if I want to scale the height, I can just multiply this whole thing by the height. So this alone would just be the heaviside function where it transitions from 0 to some value of the height at T0. But what we can do is, after we've transitioned up, we can subtract off a second heaviside function to transition back down. And so we will define our second heaviside function to transition at the delayed time, but then we're going to delay it even more by whatever the width that we want our pulse to be is. And then we'll have our 0.5. Okay, good. And then we will close our bracket for multiplying by the height. And with any luck, that should work. And so what we'll do now is we'll call, let's call, sorry, I wanted this to be, let's delete that cell. I wanted this thing to be a comment, so we'll go to markdown. And so we'll call our function and plot the results. Okay, so what we'll do is we'll select a width, and so our width will be, say, 25 nanoseconds, for example. So this is in seconds, and it corresponds to the width of our pulse. Let's call it maybe the pulse width. And then we'll say our height is going to be, it doesn't matter, it could be 5. Maybe this is a voltage pulse, so maybe this is in volts. And this could be our pulse height. Okay, and then, so T0 we've already defined above, TT we've already defined above, so we can make use of those things again. And what we'll do is we'll just do a plot of our list of times, and we'll call our pulse function, and we'll pass the right arguments, so our list, our offset time, our width, and our height. And with some luck, that should work. And so there it is. There's our pulse. We've constructed our pulse. Good. So I think the last thing that I want to do is to see if we can plot this results that we had. And so you can see that the input voltage is just the original pulse divided by 2 plus the pulse delayed in some time, 2L over S, times the reflection coefficient divided by 2. So let's prepare some of the things that we're going to need. So let's prepare some values needed to construct the voltage at the input of the transmission line. Okay, and so what are some of those things we need? We need to know, say, the load impedance at our transmission line's end. And so maybe to start, let's say this is 0, right? And so that might correspond to a short circuit. In fact, let's put in a bunch of values. So we could have a short circuit. Oh, sorry. I wanted to have ZL equals, just say some large number, which will correspond to an open circuit. And then we could have a matched. So let's say this would be a match as long as we can put in Z0 equals, say, 50, and that's going to correspond to the characteristic impedance of the transmission line. And so this is in units of ohms, and it corresponds to the characteristic impedance of the transmission line. And so we could have ZL equals Z0, and that would be a, let's call it impedance matching. And then we could also have a, I keep hitting the wrong button. We could also have ZL just equal to some arbitrary value, say maybe 10 ohms. Okay, and so we can comment out all but the ones that we are going to use, and so when we're ready for the other ones, we can have them available. Okay, the other thing we'll need is a value for the reflection coefficient, and so that's going to be equal to ZL minus Z0 divided by ZL plus Z0, and so that's our reflection coefficient. And then we need a length of our transmission line. So let's say L is equal to, doesn't matter, but we'll put 8 meters. And so that's the length of the transmission line. And then we need the propagation speed. So let's say C is equal to 3 times 10 to the 8 meters per second. So this is the speed of light. If we're thinking of a coaxial transmission line, then the speed of the signal will be slowed down because there's a dielectric between the center conductor and the outer conductor. And so how much the signal speed is reduced depends on the square root of the dielectric constant. And so let's just say that the speed of the signal is, say, 70% the speed of light is typical. Okay, so 70% the speed of light. Okay, and let's see, do we need anything else? So we have length, we have a propagation speed, we calculated the reflection coefficient, so that should be everything. Okay. So with that, then we can go here and we can say, all right, so let's finally calculate and plot V in. So maybe we can do it V math in. Okay, so V in is going to be equal to our pulse function, and we have to pass the right arguments. So it's the list of times, the delay before the pulse starts, the pulse width, and the pulse height. And then, so we had a factor of 1/2. And then it's plus gamma over 2 times the pulse function again, where we're going to pass the right arguments. But now, instead of delaying by just T0, we're also going to delay by 2 times the length of the transmission line divided by the propagation speed. So that's the time for the signal to travel twice the length of the transmission line. And then we have a width and a height. And so if I've done this right, that's everything we need. So we should be able to then do plt dot plot of this input voltage, our times on the x-axis and this input voltage on the y-axis. So let's see if we've done this right. Okay, good. So this is the short circuit condition where we have ZL equal to 0 and our reflected pulse is inverted. So now we can come back here and say, okay, well, what if I wanted to have an open circuit? And so there's our open circuit. And notice that the pulse heights are half of the 5 volts that we set. And now we could do some other funny things, like we could say, well, if we did impedance matching, then there's no reflected pulse because all of the incident signal is absorbed at ZL. And then we could try some different value of ZL, not impedance matching, but not a short or an open circuit. And we get a partially reflected pulse that's inverted. If we said ZL was not 50 ohms, but a little bit bigger than 50 ohms, we should get a partial reflection, but that is not inverted. Okay, so that's good. We can play some other games too. We could say, well, what if we made our pulse width longer? So let's just go all the way back here. And let's find T naught and say, instead of 10 nanoseconds, what if we made it, maybe not 100, maybe we can try 80. And we'll just go through and, oh, sorry, that's not what I wanted. Sorry, let me fix that. I'm trying to change the width of this pulse. So it's in here. I want to change, instead of a 25 nanosecond width, let's make it an 80 nanosecond width, or 85 nanoseconds. Okay, and so there's the wider pulse. And now we can run this thing again. And now we get some interesting behavior where there's some overlap between the first incident pulse and the reflected pulse. So if we were to make that width even wider, then we could get more of an overlap. So let's see if this works. Yeah. Okay, good. So you might say, well, what if I didn't want to do pulse propagation? What if I wanted to look at what would happen if I just had a voltage step? So a voltage just steps on and stays on. Okay, so in that case, let's just keep everything the same, but let's just make the width really, really longer, much longer than the time scale that we're looking at. So we'll just make a really long pulse. So this pulse would pulse down, but it would pulse down somewhere over here. And so we could go in and let's do this for an open circuit, just to see what happens. Open circuit. Okay. So we get this bit of a staircase effect. We could do it for also a short circuit and see what we get. And for a short circuit, what happens is it pulsed back down because what would happen is your incident signal was at a certain height, 2.5 volts, and it was staying constant at 2.5 volts. And then the reflected signal was coming back at minus 2.5 volts and staying constant. And so once they overlap, they cancel each other out. And then, of course, what we should hopefully find is that if we did impedance matching, that we have only the forward pulse, and so it's at 2.5 volts indefinitely. Okay, so that was just a fun thing. I wanted to show you how you could kind of plot some of this stuff in Python, and then that gives you the freedom to explore all of these parameters like different load impedances and different types of pulses and things like that. And so, of course, you could change the shape of your pulses to be anything you want. All right, so thanks very much. That's where I'm going to stop. I will save this Jupyter notebook and post it on the course website if anyone wants to open it up and tinker with it. Okay, thanks very much, and we'll see you in the lab.